Okay, how do optically active compounds affect plane polarized light? Plane polarized light is rotated when it travels through a solution of an optically active compound. So you put an optically active compound, usually most of the organic compounds that we deal with are solids, so especially in this chapter, so we mix them in water, create the solution, and then we pass a plane polarized light through, and it gets rotated to the left or to the right by an optically active compound. And that seems like, well, that's lovely, but who cares? Well, we'll look at that in a second. So we should just know that that's really the only way that we can look at, physically determine an optically active compound if we don't know its structure. We can do chemical reactions on it, but just physically this is a way of determining it. How do dextro rotatory and levo rotatory compounds affect light differently? Well, dextro means right, levo means left, so dextro rotatory they rotate the plane polarized light to the right. So that would be the one compound, and then its enantiomer would rotate it rotate the plane polarized light to the left. Now there's no way of telling what a compound will do when it goes into the solution until you do the experiment, but then its enantiomer has to do the opposite. So again, we have these compounds that they rotate the light to the left or to the right. One enantiomer rotates it to the left, one to the right. Big deal. But let's look a little bit further into it, why this is. If it didn't do anything else, if that's all it was, it'd be just a little scientific curiosity, and that would be the end of it. But let's talk about 4 properties of enantiomers. So two enantiomers, or a pair of enantiomers, they have identical melting point, boiling point, and density. And on the exam, I'd expect you to write it out. I know it's not fair that I abbreviate, but if you want me to write it all out and double the length of the video, we can do that. But I'm saying it out. On the exam, you'd have to write it out completely. They have the same solubility in achiral solutions. Solvents, I should say. So ones that don't have any any kind of stereochemistry going on with them, then they will dissolve the enantiomers, both enantiomers, in the same way, but different. But the enantiomers have different solubilities in chiral solutions. So or chiral solvents. So when chiral compounds are dealing with other chiral compounds, they will react differently depending on which enantiomer it is. And then they react differently to chiral reactants, whereas achiral reactants, they both react exactly the same way. And then here's the big thing. Receptor sites. So within the body, have a chirality and react accept different enantiomers, I guess differently with a precedent. So one enantiomer would come in and be completely accepted very quickly. The other would be kind of either ignored or wouldn't be able to bond as readily. That's the big difference here, that the receptor sites in the body have a chirality. So that's where the enantiomers, especially for these biochemicals that we're going to deal with, like carbohydrates, becomes desperately important. And even the way that we smell certain and taste compounds are different depending on their chirality. We have a D-carvone and L-carvone are these two compounds. One, the D-carvone has the smell and taste of the caraway seed, and so it has that grainy kind of taste to it that you expect to make a good bread. And then the L-carvone is the taste and smell of spearmint. So that's very different from each other, and that's simple, and it's the same looking molecule. They're just mirror images of each other. So even the way that we smell and taste something can be very different depending on which enantiomer that we're dealing with. And then in the body, some enantiomers are very helpful to the body. Some are not helpful at all. They just are essentially ignored by the body. That's why it's so important to study these enantiomers.